Swayam Prabha. Digital India. Educated India.
Hello, welcome to the second part of lecture 11. So in the previous part, we discussed about the frequency response of a quarter wave transformer. In this section, we are going to extend the theory, uh, the frequency response. We are trying to formulate an expression for the frequency response of not one quarter wave transformer but a series of quarter wave transformers connected in cascade. Before we obtain that expression, we need to discuss something called the theory of small reflections. So let us see what is that. So let us consider the same setup that I had discussed. So we have an our source transmission line. Okay, so this is the source, and it extends, say, to infinity. We don't say the actual voltage source is very far away. Next, we have our quarter wavelength transformer, and finally we have our load. Now, for a moment, let us suppose this may be any electrical length theta, not just limited to quarter wave. Now, here, let's say in this source transmission line, it has a characteristic impedance Z1, just like what we discussed in the previous part. This section has a characteristic impedance Z2. So at this junction, the incident wave, okay, is V1 plus. Now, when I say at this end, it means this V1 plus is a part of this transmission line. Okay. Similarly, the reflected wave at this point, at this junction, is V1 minus. Okay. At this junction, once again, the incident wave into the load is VL plus, and the reflected wave is VL minus. Okay. So our gamma L is here, gamma in is taken here, right? So from we can write an expression for gamma in as okay, or let me change this BL to V2, just be convenient for me. Okay. Now, if I want to find out the voltage at this point here, and say I call that V10, so V10 is the voltage at this end here, and say I10 is the current here. So how can I write V10 in terms of V1 plus and V1 minus? I can write V10 as equal to V1 plus V1 minus. Now see at this end or at this plane or along this line, when I write V1 plus V1 of minus, it refers to the voltage that I am seeing from this transmission line. Okay, what is the voltage that I am seeing from this transmission line? I already have these values. Can I write the voltage at this point in terms of these voltages? So if I try to write, I should get an expression like this. So this follows from the transmission line theory, where I take the distance from the load end and say the total length of this transmission line is L. Then this becomes, okay. What about the current I1 0? Now the current I can write in terms of these voltages, these incident and reflected voltage. Note that these, again I am repeating, these two terms belong to the transmission line having characteristic impedance Z1, whereas these terms belong to this transmission line which has a characteristic impedance Z2. So the characteristic impedance that I will have to consider when I write the current in terms of these values will be different from the characteristic impedance that I use when I write the current in terms of these values. What I mean is I10 can be written as V1 plus minus of V1 minus upon Z1, and that should be equal to V2 plus e raised to j beta L minus V2 minus upon not Z1 but Z2. Okay, so now coming back to this expression, if I write 1 plus gamma in, then that becomes equal to V1 plus V1 minus upon V1 plus, and 1 minus gamma in is equal to V1 plus minus of V1 minus upon V1 plus. Okay. Now, what is this term equal to? This term is equal to this value. So I can simply write this as V10 upon V1 plus, okay, which in turn, if I substitute these values, I get V2 plus e raised to j beta L plus V2 minus j beta L upon V1 plus, now which can be simplified as V2 plus e raised to j beta L 1 plus V2 minus upon V2 plus e raised to minus j2 beta L. This whole upon V1 plus. Now note this quantity is nothing but gamma L that we have defined earlier, isn't it? Because we define gamma L like this. So I'll just substitute in place of this, I'll just write it as gamma L. Okay. Similarly, I'm not deriving it, but this expression I I can write it as 1 minus gamma in is equal to, now if I substitute this quantity and put it here, then what do I get? This is equal to Z1 I10 upon V1 plus, okay, and then if I substitute the value of I10 as obtained from this expression into this equation, what I get, Z1 upon Z2 V2 plus e raised to j beta L minus V2 minus j beta L upon V1 plus, okay, which in turn, if I simplify it like I did it for the previous expression, I should get fine. Now if I take the ratio of 1 plus gamma in upon 1 minus gamma in, then from these two equations, that is this equation and this equation, my value that I obtained should be equal to 1 plus gamma L minus j beta L. Okay. So now, using that, adding the denominator to the numerator and then dividing, what I mean is if a upon I'm using this relationship, if a upon b is equal to c upon d, then this implies a plus b upon a minus b is equal to c plus d on c minus d. So if I use the same expression for this equation, I get, after some manipulation, I can show that the expression for gamma in that I get here will be equal to please do this derivation again? I'm not showing the full derivation, but I expect you to do it. Where gamma 21 is equal to so this is once again, if I go back to my figure, this is the value of the input reflection coefficient here. Now, if suppose that the mismatch between Z2 and Z1 is small, then what happens is that I can this gamma 21, this quantity becomes very small. Okay. In that case, what I can ignore this term in the denominator. Fine. So if once again, if this mismatch between Z2 and Z1 is very small, then this quantity can approximate it to be 0, and then my gamma in becomes simply okay. I should use the approximation sign. So what does this mean actually? It means, let us once again draw the diagram. So this is my source line having characteristic impedance Z1. This is my transmission line element length, finite length theta. It could be a quarter wave transformer as well. In that case, theta will be pi by 2. And finally, this is my load RL. So this is a transmission line. Right? Now, what does this equation signify in terms of physical? See, gamma in, which is taken here, has two components. One, this gamma 21, and this gamma L e raised to minus j 2 beta L. So gamma L, if suppose there were no mismatch, then this gamma 21 would be equal to 0. And in that case, gamma in would simply be equal to gamma L e raised to minus j 2 beta L, which is basically the equation that we know, isn't it? Suppose for is if Z2 is equal to Z1, then gamma in is equal to gamma L minus j 2 beta L. Okay. So this is our well-known reflection coefficient expression. As we go away from the load, recall the angle becomes more negative, and so we move in the clockwise direction. Okay. So this is something it is well known. We have discussed it earlier. But now, because of this mismatch between Z1 and Z2, there is this gamma 21 term. Okay. But what did we? But we have simplified this, right? This is a simplified expression. This was our original expression. From that, we have obtained this expression. So, what did we ignore in this whole process? See, when we consider this equation, we are only considering two things. One, that there is a reflection due to a mismatch at this junction, and there is another reflection due to mismatch, this gamma L present along this junction. We are not considering secondary reflections that may happen like this. So this, okay, so secondary reflection or tertiary reflection, this reflected wave itself again goes here and gets reflected. All these secondary and tertiary or further reflections are not considered. Only one set of reflection, one here and one here, are considered. And that is the simplification that we do. If we consider this complete expression, then that takes into account all reflections, multiple reflections, reflections of reflected waves. But here we consider only first order reflections using this expression. And that is true only when the mismatch between Z1 and Z2 is small. Okay? This is known as the theory of small reflections. This is what we call the theory of small reflections. Okay. Now, with this simplification, an assumption that the mismatch between adjacent transmission line segments is very small, we shall now develop the theory for an n-section network. Okay. So, what is an n-section network? So, an n-section, when I say an n-section network, there are n transmission line elements connected in cascade. So, let us draw that. Say this is the first section with a characteristic impedance Z1 and an electrical length theta1. This is the second section with characteristic impedance Z2 and electrical length theta1, and so on, say till we come to the nth transmission line segment having characteristic impedance Zn and electrical length theta n, and finally we have our load RL, and on this side we have our source. Okay, say the source, so this goes to infinity just like the previous case, but this source transmission line has a characteristic impedance Z0. Okay. Okay. Now suppose the reflection coefficient, input reflection coefficient at this junction, I call that gamma in 0. At this junction, I call it gamma in 1. At this junction, I call it gamma in 2. Okay. So now extrapolating, we will have at this end, we will have reflection coefficient gamma in n minus 1, and at this end we will have reflection coefficient gamma in n. Okay. So just to summarize, this setup is similar to the previous setup, except that in one transmission line segment we now have n transmission line segments, but the source transmission line element, this one, and the load part remains the same. Now, one further assumption is that all the transmission line elements have the same electrical length. So that means theta 1 is equal to theta 2 is equal to theta n. Okay. So now let us start applying that formula we obtained from the theory of small reflections and start finding the characteristic impedances, sorry, the input reflection coefficients, starting with this value. Okay, so gamma, so the gamma in, the overall input reflection coefficient starting from this point, this starting from here is equal to gamma in 0, this quantity, which is in turn equal to, that should be equal to gamma 1 0 plus gamma in 1 e raised to minus j 2 theta. Okay, so if we compare with this equation that I wrote a few minutes back, this expression, this is same. Here gamma 2 1 takes into account the mismatch between Z2 and Z1. Similarly, here gamma 1 0 takes into account the mismatch between Z1 and Z0. Gamma in here is analogous to this load reflection coefficient.